This is Vodcast 10B. In this video, we're going to talk all about enthalpy and entropy. There are two principles that govern natural events. Enthalpy is talking about energy level. It's that Q value that we looked at in video A. Energy level, if you think of nature, water always flows downhill. Moving objects always come to rest. In chemistry, electrons move down to their lower orbital levels. So what does that tell us? That tells us that energy likes to be lazy. It flows to the lower level, it comes to rest, electrons fall down, it likes low energy. And entropy, on the flip side, measures the amount of disorder. Things evaporate, water evaporates, and the particles become more disordered. If you leave a piece of ice on the counter, it would melt because liquid is more disordered than a solid. We'll talk about your room, which probably gets messier and messier, becomes a little more disordered, and how that's favored in terms of nature. So thermodynamics explores how these two principles, enthalpy and entropy, how we can apply them to different chemical reactions or chemical processes in order to determine if something's going to be spontaneous or not. More about enthalpy. Enthalpy is delta H, the change in, again, delta, the triangle, change in energy level, which is also equal to the Q that we calculated before, the total heat. So enthalpy measures the increase or decrease in overall energy level of this system. This is the thermal energy. Thermal means heat. It's either endothermic or it's exothermic. It's the energy inside of a substance. Enthalpy is extensive, just like heat. If you have more substance, you have a greater enthalpy. Enthalpy increases, this is a direct relationship. When you increase temperature, you increase your enthalpy, you increase your overall energy level, you increase your overall heat. Units for enthalpy, joules or kilojoules, or sometimes joules per mole or kilojoules per mole. We're going to talk about the first law of thermodynamics, which is the law of conservation of energy. We talked about this before. If you conserve energy, it means you're not creating it, you're not destroying it, you're only transferring it. Energy can be in the form of heat or work, and we're going to focus on the heat. You would focus on the work for physics. Chemistry talks about the heat. This Q value, or the total heat value, or the enthalpy, or the delta H, they all mean the same thing. It's the transfer of energy because of a temperature change. And each value has three parts. It has a unit, joules or calories, or sometimes kilojoules. The number, how many, there's 100 calories or there's 50 calories. And there's a sign. It's either going to be positive or negative. If heat is given off, heat is being released, that's an exothermic reactant. Heat is one of my products. When it's released, it's a negative value. We say that's exothermic. Heat is released, delta H value is negative. The flip side is true if you're putting energy into it. If heat is one of your reactants, when heat is going into, that's endothermic. If you're adding heat to your system, your delta H value is going to be positive. Exothermic, negative. Endothermic, positive. Heat given off is negative, you're releasing heat. Heat absorbed is positive, you're adding additional heat. So, we have to think again about what our system is and what our surroundings are, because which way is the heat being released or absorbed from? So first you have to define your system and surroundings. Exothermic reactions, exo, energy is released, this would be a negative delta H value. Energy is being released to the surroundings. These tend to be favored by nature. More natural events release energy into their surroundings. Endothermic changes, these would be the positive delta H, where you add energy. Energy is absorbed into the system. It's a reactant. When you absorb heat from the surroundings, it's usually not favored by nature. So here at the bottom is just a general picture, if this helps you to visualize. Our system is this big block, and the heat is either going out of exo, where delta H is less than 0, which means it's negative, or the heat is going into endothermic, where you're adding heat, so the delta H value is going to be greater than 0, or it's positive. Whatever works for you to remember that exo means out, which is a negative value, and endo, energy is coming in, heat is coming in, it's going to be a positive value. Exothermic reactions. If we're looking at this in terms of time and energy on a graph, in an exothermic reaction, the total energy of the system is lowered. It starts out high and it ends low. So you're releasing lots of energy. First, we may have to get over this point of activation energy. If you think back to day one, when I lit the bubbles on fire, I had to start the fire somehow. But the total heat or total energy of the system was a lot less at the end than it was at the beginning. We lost a lot of heat from the system to the surroundings. My energy decreased. So you start out at a higher energy, you end up at a lower energy. If we were sledding down this hill, this would be how much you have to climb up to. And you jump on your sled and you sled the whole way down the hill. That is usually favored. So this visual picture just shows you, if you're going sledding, this would definitely be favored. You only have to climb up a little bit and you get a big hill to sled down. Delta H is less than 0, or delta H is negative, because our heat is released, the energy of the system is lowered, and this reaction is favorable. A non-favorable reaction would be something that is greater than 0. When your delta H is greater than 0, it's a positive number. It's not exothermic, now it's endothermic. Endothermic reactions are when you start out at a lower energy and you have to put a lot of energy into, only get a little bit out of, and your energy level of your products is much higher than the energy level of your reactants. When you're adding energy into the system, your delta H is positive, energy into is endothermic, it's not favored. But these reactions do exist, so there has to be another driving force, and that's called entropy. Entropy has the symbol delta S. Again, change in. This is change in order or disorder of a system. It measures the disorder inside of a substance. If you think about the particles, gases would be the most disordered, followed by liquids, And then finally, the most ordered particles would be solids. This is also an extensive property. The more stuff you have, the more disorder you can have. Our units for delta S are either joules per mole Kelvin or kilojoules per mole Kelvin. Again, here's a visual picture. This is my solid, all nice and neat and arranged as particles in rows. Here's my liquid, where things start to spread out a little bit. And this would represent a gas where the particles are all over. Obviously, a gas is much, much more disordered than a liquid. And a liquid is a little bit more disordered, has a little bit more entropy than a solid. Gases completely fill the chamber, the container that they're in, because there are so many more ways for them to do that than to leave the chamber half empty. It's a greater increase in entropy. There are so many more ways for molecules to be arranged in a liquid, they can move about, than in a solid when they're tightly compact together. As I said before, solids would have the least amount of randomness because they're so ordered in how they're packed together. So changes in entropy. Here we have two pictures. This is table salt. Solid table salt, you can see how it's nicely packed together. Plus, minus, sodium, chlorine, sodium, chlorine, sodium, chlorine. And then these would be water molecules spread throughout, but with the solid still intact. And on the right, we have sodium ions surrounded by water molecules and chlorine ions surrounded by water molecules. Which would you predict would be the most random? If you think it's this side, you're correct. There's much more randomness, much more entropy when things dissolve than when they're stuck in their solid phase. There's so many more possible arrangements for the ions and water molecules once something's dissolved than when it's in the set solid phase. Okay, how about this one? Here I have 1, 2, 3, 4, 5 different particles floating around. Here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 particles floating around. Entropy, we said before, was extensive. The more stuff you have, the more randomness, the more entropy you can have. Think about your room, your closet. How many pairs of shoes do you have in your closet? And then compare that to someone else in your house. If you have 50 pairs of shoes, and your little brother has 4 pairs of shoes, whose room has the most potential to get messy, to get more random? If you took everything from your closet and threw it around your room, and everything from your little brother's closet, who only has 6 pairs of shoes and 3 pairs of pants and 12 shirts, obviously the more stuff you have, the more randomness, the more messy it can be. So, in nature, reactions tend towards the most random arrangement of particles. It wants to be random, it wants to be crazy. The arrangement that has the most particles would be the most random. And if you're comparing arrangements with equal numbers of particles, if this side had 10 as well as this side had 10, the one with the larger particles, size-wise, mass-wise, would be the most random. So, predict the sign for the following entropy change for the following processes. Now we're talking about delta S. Let's skip ahead a slide. First, nature favors greater entropy. That's more randomness, more messiness, more craziness. What does the sign mean? If you have a negative delta S, that means you're decreasing in your disorder. You're becoming more ordered. That change is not favored. What is favored is when you're becoming more disordered. Favored would be a positive delta S because you're increasing your total disorder. So entropy increases with increasing temperature because, as we said, gases are much more disordered than liquids and or solids. As you increase your temperature, particles have more kinetic energy. They're more disordered. They move about even more. So now that we know positive delta S is increase in disorder, let's go back a slide. Positive delta S is more disordered. A negative delta S is more ordered. This is not favored. Increase in disorder is favored. So, number one, solid carbon dioxide sublimes to form a gas. A solid to a gas is becoming more disordered. This would be a positive delta S. Number two, solid sugar is added to water to form a solution. That means something is dissolving. Dissolving, going from a solid into the liquid or aqueous phase, is also more disordered, so it would be a positive delta S value. Number three, iodine vapor is the gas phase, condensation changes to a liquid. Gas to liquid, we're becoming more ordered. That's not favored. That's a negative delta S value. Magnesium is a solid. Magnesium reacts with oxygen, that's the burning the bright white light, to form MgO. This is a solid. I have a solid plus a gas forming a solid. I have two things going to one, or I have a gas going to a solid. So that is not favored. That would be a negative delta S value. And number five, iron oxide decomposes. When something decomposes, it breaks down. So this case, now we have one reactant breaking down into iron plus oxygen. You're creating more particles. One thing is breaking down into two substances, creating more substances. That's a positive delta H value, or delta S value, that is favored. You're increasing the disorder of the system. So, enthalpy and entropy, they're at odds because nature favors low energy, it's lazy, but it also favors high disorder. So it's lazy, but it's craziness. It likes disorder. They both increase as the temperature increases. So enthalpy increases, which is not favored, but as entropy increases, change is favored. So how do these two combine to figure out if a reaction is going to happen or not? We're going to look at something called Gibbs energy to determine if a reaction can be spontaneous or not. All reactions have enthalpy, delta H, and entropy, delta S, associated with them. The value of your delta H, delta S, and your delta G, which stands for Gibbs energy, will determine if the reaction is spontaneous or not. Again, as a review, delta H determines if it's endothermic or exothermic. If it's a positive delta H, you're adding energy. If it's a negative delta H, you're releasing energy. Delta S values are determined by the arrangement of the particles and how disordered they are. A process that actually occurs is spontaneous. Without assistance, it's just going to naturally happen. Nature favors low energy, high disorder. High entropy, low energy. You can actually plug in your values to determine if your change is going to be spontaneous or not, if your reaction is going to be spontaneous or not. There's an equation that can be used for Gibbs energy to tell us if the reaction is going to be spontaneous or not. We're not going to use that equation. What we're going to do is make a grid. Divide your grid into 4 parts. And along the left side, we're going to have positive delta H values and negative delta H values. Along the top, we're going to have positive delta S values and negative delta S values. Now, if we look back, positive delta H means I'm adding energy to this system. Adding energy is endothermic. Negative delta H is releasing energy, or exothermic. Exothermic or endothermic, who is favored by nature? Exothermic reactions are more favorable than endothermic reactions. Releasing energy is much more favorable than adding energy to your system. Delta S, positive delta S values, this is where we increase our disorder. Negative delta S is becoming more ordered. Nature favors more disordered. So, if we look at this as a grid, nature favors more disorder, and nature favors exothermic reactions. If you're increasing your disorder by releasing energy, these reactions are always going to be favored. On the flip side, if you're putting energy in, endothermic, to create something that is more ordered, we can think about your room again. How spontaneous does your room ever become more ordered without adding any energy? Never. These reactions are never favored by nature. But your room can become more ordered. It's possible to have a negative delta S value. How is that? In order to have a negative delta S value to become more ordered, you have to put energy into the system. So your room becoming more ordered without putting energy in is never favorable. Nature's never going to allow that to happen. If we look at these other 2 boxes, where they're both positive, so if I want to increase my disorder by adding energy, which is not favored, think about a liquid and a gas. If I add enough energy, endothermic, I put enough heat into something, I can make it become more disordered. I can take a liquid and I can boil it to become a gas. But these are only favorable at very high temperatures. I can create more disorder if I put in enough energy above the boiling point. And looking at this bottom one, when they're both negative, I can create a solid. I can make something more ordered by taking the heat out of it at very low temperatures. Think about freezing. You make a liquid more ordered, you put it into the solid phase by exothermic, taking out, releasing a lot of heat. So make sure you have this grid written down. If you need more examples of how this grid works, we'll talk about that in class tomorrow.